This is section 3.5. I can find the inverse of a matrix. Inverse of a matrix. So the warm-up question says, what is the multiplicative inverse of 5? And we talked about multiplicative inverses earlier this year. So the multiplicative inverse of 5 is 1/5. And the reason it's the multiplicative inverse is if we took 5 and multiplied it by 1/5, we end up with a 1. They cancel each other off. They undo each other there. So we've learned a whole bunch about what we can do with matrices, but we haven't said anything about division. And it turns out that we can't really divide by matrices, but we can find a really clever way to get around that. So a couple of weeks ago, we talked about this equation right here, and we said normally we would solve this by dividing by 5, but let's say we couldn't use division. Did you figure out a way that we could take care of that 5, get rid of that 5 so we can solve that equation and get the x by itself? Well, if you need a hint, take a look at the warm-up here. What we could do is we could multiply by the inverse of 5. So if we multiplied this side by the inverse, multiply that side by the inverse, those things would cancel. We'd end up with x equals 6, and we'd have our answer without using any division there. Well, it turns out that we don't really need to divide by matrices very often, but when we do, we actually multiply by the inverse of a matrix, which is why we need to figure out how to find the inverse of a matrix. We're not going to use inverse matrices for anything fancy right now, but we do need to know how to find the inverse of a 2x2. Here's one mathematical definition that works for 2x2s, 3x3s, and so forth. So if A is a matrix, then A inverse, and this exponent, what looks like an exponent, is not really an exponent. When mathematicians use that right there over a matrix, what they're doing is they're talking about an inverse. We'll see some things like that in the future also. So if A is a matrix, then A inverse is 1 over the determinant times the transpose of the matrix of cofactors. Now, we've talked about cofactors before, and we've talked about determinants, but there's this word transpose here. Now, we're not going to get into anything fancy. I'm not going to explain to you where those come from. If you're interested, you're welcome to come and talk to me after class or something. But a transpose of a matrix is a right-hand pancake flip. So that's all you'll need to know for right now. Down the road, if you take a linear algebra class or something like that, then you'll learn about this. So let's talk briefly about what a cofactor is. A cofactor is a minor. We know what a minor is. And then it's multiplied by the sign associated with its position. So we talked about that checkerboard of pluses and minuses, and that's what we would use there. Not all matrices have inverses, so that's a good thing to keep in mind. In order for a matrix to have an inverse, it's got to be square so that it can have a determinant, and its determinant must not be equal to, well, if you look at the explanation right here, it says 1 over the determinant. So we're going to take 1 and we're going to divide it by the determinant. So whatever the determinant is, we're basically going to do a little reciprocal there. So can you tell what it can't be? Well, it can't be equal to 0. So can you tell why it wouldn't be equal to 0? That's because we can't divide by 0. So let's just write can't divide by 0. Okay, so that's not allowed. So that's why we've got to have a matrix that's square so that it can have a determinant, and the determinant can't be equal to 0. So otherwise, if it's not square, no inverse. If it has a determinant that's equal to 0, we won't have an inverse. So for now, again, we're only going to be finding inverses of 2x2s. And that turns out to be fairly easy. So I'm going to slide down here, and let's take a look at these steps. So it says steps for finding a 2x2 inverse. The first thing we're going to do is we're going to find the determinant of the matrix. So we've got the little formula right there. And again, if it's 0, we'll have to just say no inverse. But let's check and see what we've got on this one. So I'm going to write DET here. And then, again, the downward diagonal, we'd multiply the two of those together, so that's going to be negative 12. Then minus, don't forget the minus, that's part of the formula there. And then we're going to multiply the upward diagonal, we end up with a negative 10, so minus a minus, that turns into a big fat plus, and we end up with a negative 2. So we've got the determinant, it's not equal to 0, so we can go forward. The next thing we do is we take this matrix and we're going to do 1 over the determinant, so that's 1 over negative 2. And then what we do here is we switch the A11 with the A22. So first row, first column with second row, second column. So that's the downward diagonal. So the elements in the downward diagonal, we switch positions with the two of those. So this is going to be a negative 3 here, and this is going to be a 4 right here. And then we multiply A12 and A21. So first row, second column, and second row, first column. So that's another way of describing the upward diagonal right here. We multiply the two of those by negative 1. So they stay in the same place, they just get multiplied by a negative. So this is going to be a negative 5, and this is going to be a 2. And then the last thing that we need to do here is we just need to distribute through. So we multiply 1 over the determinant and we simplify. So we go ahead and we multiply the two of these and we end up with this. If I do a negative times a negative, I get a positive. So this is going to be 3/2. Negative times a negative, we get a positive, so we get 5/2 right here. And then we have negative times a positive, that's going to be negative. And 1/2 of 2 is 1, so we're just doing some scalar multiplication here. And then negative 1/2 times 4 is going to be negative 2, and this right here is the answer. So the way we'd write the answer would be A inverse is equal to, and then I'll set up this 2 by 2. So 3/2, 5/2, -1, and -2. And I'll go ahead and circle that. That would be the answer. So we're going to slide down here and we'll take a look at the last one on this page. And let's see what we've got here. It says, given B, find B inverse. And again, that's the way we say that. It's not an exponent, so keep that in mind. So here's what we're going to do on this one. We're going to take this and we're going to find the determinant. So I'm going to write DET. We're going to multiply the downward diagonal. When we multiply the downward diagonal, we get -30. Write the minus, again, because that's part of the formula. And then we're going to multiply the upward diagonal here, so that's going to be a 6. So we end up with -36. So we have a determinant that's not equal to 0, so let's go ahead. So I'm going to do 1 over the determinant, so this is 1 over -36. And then again, here's how this works. We're going to switch the 2 in the downward diagonal, so this is going to be a 5 and a -6. The upward diagonal, they stay in the same place, they just get multiplied by a negative. So this is going to be a -3, and this is going to be a -2, and then we'll distribute through. Now, to save myself a little bit of space, I'm going to write B inverse, and then, whoops, let me make that look a little bit better. So I'm going to close this off right here, and then when we multiply here, we get a -536, nothing to reduce there. Negative times negative is going to be a positive, and we get 1/36. So we've got a 3 over 36. We can reduce that. 3 goes in there once. 3 goes in there 12 times, so that one's not too bad. The next one, we're going to have a positive. So this is going to be a 2 over 36. I'd get 1/18. And then the last one, we're going to have a 6 over 36. This is going to be 1/6. So this right here is the answer to example 2. That is B inverse. If this is B, that's B inverse. Okay, we're on the second side, and the instructions are the same here. It just says find the inverse for each matrix below. If it doesn't exist, we just need to give a reason why that it doesn't. So the first thing we're going to do is we're going to find the determinant. So I'm just going to go multiply that downward diagonal. We get 21 minus the upward diagonal. That's going to be 20, so we get a 1. Love it when this happens because we have a 1 over a 1. 1 over the determinant in this case is just 1. And then we switch the downward diagonal, so we have a 3 and a 7. These two stay in the same place. We just multiply them each by a negative. And then we distribute through. So if this were the case, we're multiplying through by a 1, so we've got A inverse is equal to, this would just be 3, -5, -4, and 7. So let's go ahead and grab that. We'll circle the answer and just continue on here. It's a very simple process. We just need to make sure that we've got this down. So we'll multiply the downward diagonal here. So the determinant in this case, we've got a -24, write a minus. The upward diagonal, that's -24 also. That's -24 plus 24, so that's a 0. So we're going to say no inverse. Okay, no inverse, and we just say that the determinant is equal to 0. That's the reason why. So we'll slide down here, take a look at the next one. So on C, let's see what we've got here. Again, determinant's the first thing. We've got 12 times 12, that's a 144. Then we're going to subtract when we multiply the upward diagonal. When we multiply there, we also get 144. So again, we end up with a determinant equal to 0. So there's no inverse on this one. Gosh, we love it when that happens. That's great. You will have a couple like that on your assignment. Again, I'll just write that the determinant equals 0. That's our reason. And let's go through here. I'm going to write D inverse here. And then let's see, we've got to find the determinant here. Let's see, we multiply downward, we get a -21, minus, when we multiply upward, we get a 24, so we end up with a -45, kind of an ugly number there, so we're going to have -1 over 45 here. And then again, downward diagonal, they switch places, so this is 7 and -3. The upward diagonal, they get multiplied by a negative, so this is -3 here and a -8 there. So we'll go ahead and multiply through. So this, let's see if anything simplifies. A 7 over a 45, that's not going to simplify, so that's going to be -7/45. These three elements right here, they're all negative, so when we multiply them by a negative, they're going to be positive. And if I've got a 3 over a 45, 3 goes in here 15 times, so this would be 1/15. This is going to be 1/15. And then this last one right here, that's not going to reduce at all. We end up with 8/45. Whoops, 8/45. Let me make that look right there. Okay, so we've got that one taken care of. Let's slide down here and take a look at E. Now the problem with E, you'll notice this isn't even square. So the answer on this one is no inverse. And the reason is not a square matrix. Doesn't even have a determinant. And again, you can see what the problem is. We're leaving off those two numbers on the end there, so we don't get any information about those. So I'm going to slide down here to the bottom, and I've got one last thought question here for you. You found A inverse in example 3A above, and then it says now find A times A inverse. So let's slide back up here, and let's figure out what that was. So we've got 7543. 7543, there we go right there. And then the inverse was 3, -5, -4, 7. So 3, -5, -4, 7. Now, we've got some matrix multiplication to do here, so let's just go ahead and take a look at that. This is a 2 by 2, and this is also a 2 by 2. Remember, the inner dimensions have to be the same. If those are the same, then the resultant has the outer dimensions. So this is going to be a 2 by 2. And I like drawing those little lines right here so I know how many elements that I've got to find. So this is first row, first column. So we're going to multiply the first row with the first column. So I'm going to multiply 7 times 3, that's 21. And then we're going to add 5 times -4, that's a -20. So 21 minus 20, this would be a 1 right here. Now, this one is in the first row, second column, so we're going to multiply the first row with the second column. And again, we do this correspondingly. We talked about the karate chop method, if you were with me for that. So we would multiply the 7 times the -5, so that'd be -35. The 5 times the 7, that's a 35. -35 plus 35 is 0. And we get kind of an interesting pattern here. Notice what happens on this next one. This is second row, first column. So I'm going to take the second row and multiply it with the first column right here. So this is going to be 4 times 3, that's 12. 3 times -4, that's -12. So when we put those together, we end up with a 0. Now, you may remember something like this before. You might want to take a guess at what goes right there. Let's just double check and make sure that your guess is right. So I'll give you just a second to take a guess and see if you can remember that. But let's go ahead and multiply here. So this is second row, second column. Second row multiplied with the second column. This is going to be 4 times -5, that's -20. 3 times 7 is 21, so when you do -20 plus 21, we end up with a 1. So what we have here is the I2 matrix, the 2 by 2 identity. This is what we get. So when we multiply the matrix by its inverse, we end up with the equivalent of a 1. So do you notice anything about the resultant? It's the identity. So let's just write down that it's the matrix equivalent of a 1. So when we multiply the two of these together, this would be like multiplying by A, and this would be like multiplying by the inverse of A. That's literally what we're talking about. It's kind of like the warm-up question where we had 5 times 1/5, and we end up with 1. Okay, so this is why we study the inverses of matrices, because they allow us to undo multiplication. They allow us to undo matrix multiplication. So go ahead and do the self-assessment right there, and then get started on the assignment.